Hello, cosmic travelers, and welcome back to the channel. Have you ever looked up on a clear winter night, found that famous hourglass of stars we call Orion, and let your gaze drift just below his belt? Right there, in what the ancients saw as his sword, hangs a faint, fuzzy little smudge of light. To the naked eye, it's just a hazy star. But that tiny, unassuming patch is, in reality, the gateway to one of the most spectacular, violent, and beautiful places in our entire galaxy. What you're seeing is not a single star, but a dazzling, chaotic, luminous cloud, a celestial forge where stars are born by the thousands. This is the Orion Nebula. For centuries, it's captured our imagination, and for the last few decades, our most powerful telescopes have been trained on it, unraveling its secrets. And what they've found is a story more epic than any myth, a story of birth and destruction, of immense forces sculpting cosmic landscapes, and of the very origins of solar systems like our own. Today, we're going on a journey. We're going to dive headfirst into that glowing cloud, traveling 1,344 light-years from your screen right into the heart of a stellar nursery. We'll discover how this nebula formed, how it gives birth to stars, some of which are utterly terrifying in their power, and what incredible futures and inevitable endings are written in its swirling gases. We'll leave no stone unturned. So, if you're ready for an adventure, make yourself comfortable. And if you want to join our community of space enthusiasts, be sure to hit that like button, subscribe to the channel, and most importantly, let us know in the comments where in the world you're watching from and what time it is for you right now. It's always amazing to see our global family of stargazers come together. Now, let's begin. The Orion Nebula, also known to astronomers as Messier 42, or M42 for short. It's often called the jewel in the sword of Orion, and once you see a detailed image of it, you understand why. But to truly appreciate this place, we need to understand that the gorgeous glow we see in photographs is just the bright, visible tip of a colossal, hidden iceberg. When you look at a magnificent photograph of M42, and oh, we have some stunning ones from telescopes like Hubble, you're seeing the part that's shouting. It's lit up, it's energized, it's putting on a spectacular light show. But space, deep space, isn't usually like that. Most of it is profoundly, utterly dark and silent, and the raw material for making stars isn't shiny neon gas. It's more like a frigid, invisible fog. This is where we meet the true parent of the Orion Nebula, the Orion Molecular Cloud Complex. Think of it this way. Imagine you're flying over a continent at night. You see the cities glittering below, clusters of light like Los Angeles or the glowing sprawl of Tokyo. Those are the nebulae, the bright spots. But what lies between them? Miles and miles of dark countryside, forests, mountains, and plains, invisible in the darkness. The Orion Nebula is one brilliant metropolis. The Orion Molecular Cloud Complex is the entire dark continent it sits upon. This complex is a monster. It's not a single neat cloud. It's a sprawling, tangled network of gas and dust that sprawls across hundreds of light years, covering much of the constellation Orion itself. Hundreds of light years. The nebula we see is maybe 30 or 40 light years across, so the visible part is just a tiny district in a colossal, invisible megacity. And what is this cloud made of? It's not like a cloud on Earth. It's far, far emptier than the best vacuum we can create in a lab on Earth. But across such immense distances, that scarcely there stuff adds up. The main ingredient is simple hydrogen gas, the most basic, ancient element in the universe. Floating alongside it are microscopic grains of dust, like fine soot or sand, made of things like carbon and silicate rock. This dust is unbelievably important. It's what makes the cloud dark. You see, this cloud is cold. We're talking only about 10 degrees above absolute zero, the coldest temperature possible. At that temperature, the hydrogen atoms link up into molecules, two atoms paired together, which is why we call it a molecular cloud. And in that deep cold and darkness, the dust grains act like a cosmic insulation blanket. They block out the faint light from distant stars that might try to sneak through. They absorb any warmth. So, deep inside this cloud, it is pitch black and frigid, a silent, frozen, lightless realm where time seems to stand still. For millions upon millions of years, nothing much happens. The cloud just drifts through the galaxy, a ghostly iceberg in the cosmic sea. But stillness is only ever temporary. The universe is a dynamic, often violent place. A structure this big can't just drift forever without something bumping into it. The trigger, the alarm clock that stirs this frozen giant from its slumber, could be a few different things. Perhaps as our solar system and this cloud wheel around the center of the Milky Way galaxy, the cloud drifted through one of the galaxy's majestic spiral arms. These arms aren't solid, but they are regions where the density of stars and gas is a bit higher, where gravitational forces are a bit stronger. It's like sailing a boat into a region of stronger currents and tides. The extra gravitational push and pull can squeeze the cloud, creating internal ripples and eddies. Or the trigger could be something far more dramatic. Somewhere else in the galaxy, a massive star, much bigger than our sun, reached the end of its life. It didn't fade quietly, it exploded. We call this a supernova, and it is one of the most violent events in the universe. The star blasts itself apart, and for a brief moment, it can outshine its entire galaxy. That explosion sends a titanic shockwave racing through space at a significant fraction of the speed of light. Imagine the most powerful tsunami you can conceive, but made of pure energy and force, rolling through the vacuum. Millennia later, that shockwave slams into our quiet, dark Orion molecular cloud. It's a cosmic tsunami crashing onto a frozen shore. The sudden, immense pressure from outside acts like a giant hand, giving the entire cloud a tremendous squeeze. It compresses the gas and dust, not uniformly, but in a chaotic, turbulent way. Think of it like pushing on a giant pillow. Some parts get compacted more than others. Ripples form. Pockets of higher density emerge from the general fog. And here, in these newly compressed, extra-dense pockets, the rules of the game change completely. We've arrived at the moment where the universe's most patient and powerful force takes center stage. Gravity. Gravity is the great gatherer. It's an attraction between all things that have mass. Normally, in the thin haze of the cloud, the gravitational pull between individual atoms is incredibly weak, but when you pack trillions upon trillions of them into a much tighter space, their collective pull adds up. It becomes a force to be reckoned with. Once a pocket of gas reaches a certain critical density, its own self-gravity becomes stronger than the internal gas pressure and any other forces trying to keep it puffed up. It reaches a tipping point, and then it begins to fall. It collapses. It starts to fall in on itself. This collapse isn't neat and orderly. Because the cloud is turbulent and lumpy, it doesn't collapse as one single ball. Instead, it fragments. It's like watching a breaking wave. One large mass splinters into many smaller ones. The giant, dense pocket shatters into countless smaller, even denser knots and clumps. Each one of these collapsing, spinning knots of gas and dust is a potential star in the making. Astronomers have a special name for these stellar embryos. They call them protostars. Now, we can zoom in on one specific region of the vast Orion molecular cloud complex to a particular dark lane known as the Orion A cloud. Within this cloud, about 1,344 light-years from Earth, one of these episodes of collapse and fragmentation kicked off relatively recently. And it didn't just create one or two stars, it created a whole bustling factory of them. The heart of this factory, the brightest, most active workshop, is what we now point our telescopes at and call the Orion Nebula. So, when you look at M42, you are not looking at the beginning of the story. You were looking at the spectacular middle act. You were seeing the aftermath of that gravitational collapse, now lit up by its most brilliant and violent products. The dark molecular cloud is the quiet, dark countryside. The nebula is the glittering, noisy city that was built from its resources. And that city is now tearing apart the very countryside that gave it birth. Because here's the brilliant twist. The stars that form in these dense clumps, especially the really big, hot ones, are not polite tenants. They are revolutionaries. At the core of the Orion Nebula is a tight-knit group of such revolutionaries, the Trapezium cluster. These are 4 massive, searingly hot young stars with more siblings hidden around them that are only about 1 million years old, absolute infants compared to our 4.6 billion-year-old sun. These trapezium stars are like cosmic blowtorches. They flood their surroundings with an intense flood of ultraviolet radiation. This UV light is so energetic that it doesn't just illuminate the cold hydrogen gas left over from the cloud, it ionizes it. It blasts the electrons right off the hydrogen atoms, creating a swirling, glowing plasma. It's this process of ionization that makes the nebula emit its own light. That's why it's called an emission nebula. The UV radiation carves out a gigantic cavity in the surrounding molecular cloud, like a blowtorch melting a hole in a block of ice. This is the blister we see. The brilliant Orion Nebula is essentially a vast glowing cavity that has been hollowed out of the side of the dark, cold Orion A molecular cloud. The dense wall of the original cloud still surrounds it on the sides and behind, but facing Earth, the blister has burst open, giving us a breathtaking view right into the stellar nursery. The trapezium's fierce winds and radiation are also doing something else. They are destroying the nearby star-forming material. They are blowing away the gas and dust before it can collapse into new stars. In that immediate neighborhood, star formation is being brutally shut down. But, like any powerful force, it has a double edge. As these stellar winds push outwards, they slam into the surrounding walls of the molecular cloud. They pile up the gas and dust there, compressing it into new, incredibly dense ridges and pillars, like the famous Pillars of Creation in other nebulae, but right here in Orion. And in these new pressurized ridges, the conditions become perfect for, you guessed it, the next generation of star formation. So the massive stars both end the story in their immediate vicinity and write the first chapter for stars yet to be born farther out. This brings us to the final, beautiful point about this tip of the iceberg. Because the dark cloud is so vast, the nebula's activity is just a local phenomenon. While the trapezium stars are clearing out their little cavity, the rest of the Orion molecular cloud complex carries on. It is still dark, still cold, and still collapsing in other places. New protostars are flickering to life in the darkness, hidden completely from our optical telescopes by that ubiquitous, obscuring dust. They are the very young red objects partly hidden in the cloud, waiting to be revealed, that astronomers talk about. To see them, we need eyes that can peer through the dust. We need infrared telescopes. Infrared light has longer wavelengths than visible light. Think of visible light waves as tiny marbles that bounce right off dust grains. Infrared waves are more like big, lazy beach balls that roll right around them. Ground-based giants like the Very Large Telescope, VLT, and space telescopes like Hubble with infrared cameras, Spitzer, and now the James Webb Space Telescope, JWST, have done exactly this. They have peered straight into and behind the glowing nebula, into the heart of the dark cloud itself. What they've found is the true hidden scale of the nursery. They've found not just the 4 bright trapezium stars, but a whole bustling cluster of nearly 1,000 young stars crammed into a small space. They've seen the faint glows of infant stars still swaddled in their dusty cocoons. They've spotted powerful jets of material screaming away from the poles of these baby stars, slamming into the cloud and creating glowing shock waves. And, most wonderfully, they have discovered hundreds of proplyds, protoplanetary disks. These are flat, spinning pancakes of gas and dust swirling around the newborn stars. Seen in silhouette against the bright nebula or glowing of their own heat in the infrared, they are the raw construction sites for solar systems. Planets are forming there right now in that hidden darkness. The trapezium cluster we are talking about for some time now, worth more discussion here. In trapezium cluster, with a backyard telescope, you might see the four brightest as a little trapezoid of brilliant blue-white points of light. But there are actually hundreds of stars here, crammed into a space smaller than the distance between our Sun and its nearest stellar neighbor. They are the newborns of this nursery, and they are outrageously hot, young, and energetic. Now let's meet the star that runs the entire show. If the Orion Nebula is a dazzling city of light, then one particular star is its power grid, its streetlights, and its demolition crew, all rolled into one. This is Theta 1 Orion C, the undisputed monarch of the trapezium cluster. Calling it a star almost feels insufficient. It is a cosmic engine of staggering ferocity. Think of our Sun. It's a comforting, warm yellow ball that sustains life. Theta 1 Orionis C is a different kind of beast entirely. It's a searing blue-white point of fury. Its surface isn't just hot, it is screamingly, violently hot, raging at about 39,000 to 40,000 Kelvin. To put that in perspective, our Sun's surface is a relatively cool 5,800 Kelvin. If you could place Theta 1 RAC in the center of our solar system, its surface would extend roughly to the orbit of Mercury, and its unimaginable radiation would sterilize and vaporize every planet out to the Kuiper Belt. Its physical stats are simply monstrous. It holds about 33 to 40 times the mass of our Sun packed into a body only about 10 times wider. But mass and size aren't where its true power lies. It's in its luminosity, its total energy output. Theta 1 Orionis C pumps out a staggering 204,000 to 210,000 times more light than our Sun. It is responsible for generating roughly 85% of all the ultraviolet light pouring out of the entire trapezium cluster. This isn't just sunlight dialed up. This is a fundamentally different kind of energy. And here is where the magic and the violence of the Orion Nebula truly begins. That incredible flood of energy isn't mostly in the visible light we see, it's in the ultraviolet UV part of the spectrum. UV light is far more energetic than visible light. It's the same kind of radiation that gives you a sunburn, but Theta 1 Orionis C produces it with the intensity of a cosmic blowtorch. This star doesn't just shine on the gas cloud it was born from, it assaults it. When these torrents of UV photons slam into a calm neutral hydrogen atom floating in the nebula, they do something brutal and beautiful. They have so much energy that they blast the electron right off its parent proton. This process is called ionization. You're turning a neutral atom into a positively charged ion, the proton, now alone, and a free negatively charged electron. The serene cloud of gas is suddenly transformed into a seething, chaotic maelstrom of charged particles. We have a name for this superheated, electrified state of matter: a plasma. Now, nature abhors imbalance. That liberated electron zipping through space is desperate to find a new proton to call home. Eventually, it will be recaptured, but to settle down, it has to shed the extra energy that's keeping it excited. It does this by spitting out a tiny packet of light, a photon. And this is the glorious punchline. When an electron gets recaptured by a hydrogen proton, the photon it releases is most often a very specific shade of red. This precise atomic process is what paints the vast, glowing canvas of the Orion Nebula with its characteristic crimson hues. But the universe's palette isn't limited to red. Floating in that cloud alongside the hydrogen are traces of other elements forged in ancient stars: oxygen, sulfur, nitrogen. When they get ionized and their electrons recombine, they give off their own signature colors. Oxygen contributes beautiful blue-green tints, while sulfur adds deeper reds. It's this combination of elemental glows, all triggered by Theta 1 Orionis C's UV onslaught, that creates the ethereal, multicolored masterpiece we see in photographs. A nebula that glows from within like this, powered by stellar radiation, is officially called an emission nebula. The Orion Nebula is one of the finest and closest examples in our sky. Yet Theta 1 Orionis C isn't done. It also unleashes a stellar wind of unimaginable ferocity. This is a supersonic stream of charged particles screaming off its surface. While our sun has a gentle solar breeze, the wind from Theta 1 Orionis C is 100,000 times stronger and blasts outward at about 1,000 kilometers per second. This wind acts like a cosmic bulldozer. Research using the Sophia Airborne Observatory has shown that this wind has plowed up a gigantic bubble in the heart of the molecular cloud, clearing out gas and dust for light years around. It's literally blowing away the raw material for making new stars, putting an abrupt end to star formation in its immediate neighborhood. This process, where a star's own energy and wind dramatically alter its birth environment, is called feedback. Theta 1 Orionis C is the feedback king. Oh, and one more fascinating detail. Theta 1 Orionis C is a complex multiple star system. The primary star, C1, has at least one massive companion, C2, which is itself a hefty star with about 9 to 12 solar masses. They orbit each other in a highly elongated, eccentric dance that takes about 11 years to complete. There's even intriguing evidence from spectroscopic studies that there might be a third, much smaller companion in an even tighter orbit, making this a potentially triple-star system. So the powerhouse illuminating the nebula is itself a dynamic, interacting gravitational tango. Now, here's the incredible twist in our story. All that breathtaking visible light we've been talking about, the glorious reds and blues captured by the Hubble Space Telescope, is both a revelation and a lie. It's a beautiful lie, but a lie nonetheless. It hides as much as it reveals. The heart of the trapezium cluster is shrouded in the very substance that created it, dust. Not household dust, but microscopic grains of carbon and silicate, finer than smoke. To our eyes and to telescopes that see only visible light, this dust is an opaque, glowing curtain. It blocks our view. It's like trying to peer into the heart of a raging forest fire by looking at the brilliant flames. You see the effect, but you miss the burning logs and the intricate structure of the blaze at its core. The most interesting action, the actual birth of stars and planets, is happening behind that brilliant curtain. But astronomers have a secret weapon, a way to see the unseeable. Dust has a critical weakness: infrared light. Let's break this down with a simple analogy. Think of the dust grains as tiny boulders in a stream. Visible light waves are like fine, fast-flowing water. When this water hits a boulder, it splashes, scatters, and gets blocked. It can't get through. That's why dust looks opaque. Infrared light waves, however, are different. They have much longer wavelengths. Imagine them not as water, but huge, slow, rolling ocean swells. When a massive swell encounters a boulder, it doesn't splatter, it just rolls right over it and continues on its way. The boulder is too small to disrupt the big, lazy wave. This is exactly how infrared light behaves with cosmic dust. The waves are so long that they simply pass around the tiny dust grains without being scattered or absorbed. Infrared light can pierce through veils of dust that are completely impenetrable to our eyes. So, how do we catch this infrared light? We use special telescopes. On the ground, instruments like the Very Large Telescope in Chile are equipped with infrared cameras. In space, we've sent up pioneers like the Spitzer Space Telescope, and most famously, the Hubble Space Telescope itself, which has powerful infrared-sensitive instruments. And now, we have the James Webb Space Telescope, JWST, which is essentially a gigantic, ultra-sensitive infrared eye designed to do exactly this kind of work. When astronomers point these infrared eyes at the seemingly solid heart of the Orion Nebula, the dusty curtain doesn't just become translucent, it vanishes. And what they have found on the other side is a scene of such frantic, chaotic, and beautiful activity that it has rewritten our understanding of stellar nurseries. First, they found stars. Not just the 4 bright trapezium stars, but hundreds more. The Orion Nebula cluster, of which the trapezium is just the bright core, is packed with over 1,000 young stars, crammed into a region only about 4 light-years across. That's the same distance from our Sun to its nearest stellar neighbor. Most of these stars were completely hidden, swaddled in thick cocoons of gas and dust, still in the final stages of gravitational collapse. In infrared light, they glow like buried embers. Second, they witnessed the violent birth cries of these infant stars. As a baby star or protostar forms, it doesn't just sit there quietly gathering material. Complex magnetic fields channel some of the infalling gas into incredibly focused, narrow beams that fire away from the star's poles at supersonic speeds, hundreds of kilometers per second. These are called jets. When these hypersonic jets slam into the slower-moving gas of the surrounding cloud, they create violent shock waves that heat the gas and make it glow. Astronomers call these glowing knots Herbig-Haro objects. They are like temporary signposts, flashing beacons that scream, "A star is being born right here." Seeing these jets in Orion confirmed that the messy, dynamic process we theorized about was not just real, but common. But the most profound, the most soul-stirring discovery of the infrared revolution was the third one. They found the proplyds. Short for protoplanetary disks, proplyds are the missing link in the story of our own origins. Imagine a newborn star. Around it, the leftover gas and dust from its formation don't just float away. Instead, they settle into a vast, flat, spinning pancake, a disk that can stretch for distances many times greater than our entire solar system. This is a proplyd. In the Orion Nebula, Hubble and other telescopes have found dozens of these proplyds. Some are seen in silhouette as dark, compact disks against the bright background of the glowing nebula, like black bugs on a neon sign. Others, seen in infrared light where the dust itself glows warmly, appear as bright, glowing rings or ovals. They are the raw construction sites for solar systems. Inside a proplyd, the magic of planet building begins. Microscopic dust grains floating in the gas gently bump into each other. Electrostatic forces make them stick like cosmic Velcro. Dust specks become grains, grains become pebbles, pebbles become rocks. Through countless collisions and gentle mergers, these rocks grow into planetesimals, the building blocks of planets. Over millions of years, gravity takes over, pulling the largest of these planetesimals together to form terrestrial planets like Earth, while in the colder outer regions of the disk, ice and gas coalesce to form giants like Jupiter and Saturn. The discovery of so many proplyds in a single nearby nebula was a revelation. It provided visual, undeniable proof that the formation of planetary systems is not a rare accident. It is a common, natural, and inevitable byproduct of starbirth. Wherever a star like our Sun forms, a disk of material will likely form around it, and from that disk, planets will coalesce. Our own solar system was once just an anonymous proplyd swirling in the dusty light of some forgotten nebula 4.6 billion years ago. Looking at the proplyds in Orion is like looking back in a cosmic mirror, witnessing our own deepest past. So, the next time you see a glorious visible light image of the Orion Nebula, remember this duality. The beautiful colors are the magnificent side effect, the glowing signboard of the cosmic factory. But the real work, the messy, creative, planet-forging labor is happening in the hidden, dusty back rooms, revealed only by the gentle, penetrating touch of infrared light. We see the brilliant advertising, but only with special tools can we step inside and watch the assembly line in action. Let's pull our focus back for a second. We've been marveling at the incredible light show and peering into the hidden nurseries, but now it's time to talk about the weather. And in the Orion Nebula, the weather forecast is always the same. Ferocious winds with a chance of total annihilation, followed by potential new beginnings. We've met the star responsible for this weather, Theta 1 Orionis C. We know it's hot, we know it's bright, but its influence goes far beyond just being a glorified light bulb. This star is a cosmic engine, and like any powerful engine, it produces exhaust. In this case, that exhaust is a stellar wind. But don't picture a gentle breeze. This is a supersonic hurricane of charged particles, protons and electrons, screaming off the star's searing surface at about 1,000 kilometers per second. To put that in perspective, the solar wind from our sun travels at a leisurely 400 to 500 kilometers per second. The wind from Theta 1 Orion C is not just faster, it's 100,000 times more powerful and dense. It carries a staggering amount of raw mechanical force. For a long time, astronomers theorized about the impact of such a wind. They could see its effects indirectly, like watching trees bend in a storm you can't see. But to truly map it, to measure its power and see its shape, they needed a special kind of observatory. That's where SOFIA comes in. SOFIA, the Stratospheric Observatory for Infrared Astronomy, was a brilliant piece of engineering, a giant 2.5-meter telescope mounted inside a modified Boeing 747 aircraft. By flying at altitudes above 40,000 feet, it soared above 99% of Earth's atmospheric water vapor, which blocks the specific kind of infrared light crucial for this detective work. SOFIA was equipped with an instrument called Upgrade, a high-resolution spectrometer. Think of it not as a camera that takes pretty pictures, but as a cosmic tuning fork and speed gun combined. It was tuned to detect a faint specific fingerprint of light emitted by ionized carbon atoms, called the Ci2 line at 158 micrometers. Why this specific light? Because ionized carbon is a perfect tracer for the chaotic interface where a stellar wind slams into cold neutral gas. It's the glow of the collision itself. When astronomers pointed SOFIA at the heart of Orion, the data that came back was a revelation. It showed that the wind from Theta 1 Ori C isn't just blowing randomly. It has sculpted space. It has blown a gigantic spherical cavity right in the middle of the molecular cloud. This cavity is a bubble, and it's enormous, roughly 2 parsecs, or about 6.5 light-years across. That's a hole in space nearly twice the distance from our sun to its nearest stellar neighbor. The walls of this bubble are made of the stuff that got bulldozed. The wind has swept up a vast shell of gas and dust, shoving it outward. This shell has a truly astronomical mass, about 2,600 times the mass of our entire sun, and it's expanding outward, away from the trapezium stars, at a steady 13 kilometers per second. This structure even has a name that evokes its delicate, torn appearance, the Orion Veil. It's the shimmering, rippled curtain of neutral gas you see at the edges of the nebula in deep images, and now we know it's not just hanging there, it's being violently pushed. This is the literal ground truth of stellar feedback. Theta 1 Ori C is feeding back its incredible energy into the environment that created it, physically rearranging the furniture. And this is where the story gets truly fascinating, because this action has 2 completely opposite, contradictory outcomes. It's the ultimate cosmic double-edged sword. On one edge, it's a sword of destruction. Imagine you're a modest little pocket of gas and dust, just starting to feel the sweet tug of gravity, beginning that slow, beautiful collapse into a new star. You're a stellar dream in the making. But you had the misfortune of forming too close to Theta 1 Ori C. Before your dream can even take shape, the hurricane hits. That relentless supersonic wind doesn't gently nudge you, it blasts you. It tears the very atoms of your gas cloud apart, scattering them into the void before gravity can get a proper grip. It's like trying to build a sandcastle as the tide is rushing in. The material is simply swept away. This is why, in the immediate neighborhood of the trapezium, in that cleared-out cavity, Theta 1 Ori C has no stellar siblings its own age. It is, in effect, an only child in its own backyard. It used the material around it to build itself, and then its first act of cosmic toddlerhood was to throw a tantrum so violent it destroyed the nursery and prevented any other babies from being born nearby. Astronomers call this negative feedback. The star's own activity suppresses further star formation in its vicinity. But now, let's look at the other edge of the sword. Let's follow that wind as it races outwards. It smashes into the surrounding molecular cloud with unimaginable force. It doesn't just scatter that material. At the leading edge of the bubble, it piles it up. Think of a cosmic snowplow. As the plow blade pushes forward, it doesn't make the snow disappear. It compresses it into a dense, packed ridge at the edges of the road. That's exactly what the stellar wind does. It pushes the gas and dust of the Orion veil into incredibly dense, compressed walls, ridges, and the famous pillars we see in Hubble images. And in the cold, dark physics of space, density is destiny. When you take a diffuse cloud and crush it together, you increase the local gravity. You also create shock waves that ripple through the compressed material. These two things, increased density and shockwave turbulence, are the very triggers for gravitational collapse. They are the seeds of stellar formation. So, while Theta 1 Ori C is a destroyer in its own home, it is also a creator in the suburbs. Out on the frontiers of its bubble, in those dense, compressed ridges, conditions become perfect for a new wave of star formation. It's like a gardener pruning a bush. The violent trimming in the center seems destructive, but it encourages new, lush growth around the edges. The star's fury is sculpting the next generation. This is the flip side of feedback, triggered star formation. Now, the SOFIA and follow-up observations have shown this process in stunning detail. They found that within the massive, mostly atomic shell of the veil, there are small, incredibly dense globules of molecular gas. These globules are tiny, only about 10,000 astronomical units across, and AU is the distance from Earth to the Sun, and they weigh in at about 1 solar mass or less. They are the compressed seeds. In fact, one of these globules already coincides with a known protostar, a star caught in the very act of being born. It's the first direct clue that this triggered formation might be real, happening right now on the edges of the bubble blown by the nebula's most brilliant star.
This is the stunning, self-regulating cycle of a stellar nursery. The most massive stars are born from the cloud, and their first acts of brilliance and violence then proceed to tear that cloud apart, simultaneously shutting down star formation in their orbit while potentially kickstarting it farther out. They shape their own birth environments and write the rules for their future siblings. Theta 1 Orionis C is both the tyrant and the architect of its domain. And all of this incredible, violent, creative drama is happening in the blink of a cosmic eye. This brings us to the second mind-bending part, the sheer, incomprehensible scale of time involved. The stars we are talking about in the trapezium cluster are not just young, they are infants, newborns. Their estimated age is roughly 1 million years. Let's try to wrap our minds around that number. 1 million years. It sounds like a long time, doesn't it? Human civilization is only about 10,000 years old. 1 million years ago on Earth, our ancestors were early hominids, just beginning to walk upright. But in the life of a star, especially one like our Sun, 1 million years is nothing. Our Sun is about 4,600 million years old. That's 4.6 billion. So the trapezium stars are 4,600 times younger than our Sun. The text gives us a beautiful analogy. If we compressed the Sun's current lifetime into a 40-year human lifespan, the entire active, fireworks-filled period of star formation we see in the Orion Nebula, the births, the winds, the carving of bubbles, would have lasted only about 1 month. Let's sit with that. Our middle-aged, stable, reliable Sun has had a 40-year life so far. The Orion Nebula's starring act is a single, frantic, brilliant month within that life. Theta 1 Orionis C, that mighty engine driving the whole show, is a toddler less than a month old in this scale. Its bubble, the 6.5 light-year wide cavity, is estimated to be only about 200,000 years old. In our human lifespan scale, that's a structure it created in just the last 2 or 3 days. This scale changes everything about how we see that fuzzy patch in Orion's sword. We are not looking at an ancient, eternal monument. We are witnessing a live broadcast of a recent, ongoing, and fleeting event. We have a front-row seat to the opening night of a stellar cluster. The light that left Theta 1 Orionis C and entered Sophia's telescope 1,300 years ago was emitted from a star that was, in cosmic terms, practically fresh out of the womb. The bubble it was blowing was brand new. The proplids we see around other stars are not relics. They are active construction sites where planets are, at this very moment, coalescing from dust. We are watching a snapshot of a place that looks almost exactly the way our own solar system neighborhood looked 4.6 billion years ago, in its first furious month of existence. This timeline also frames the future with heartbreaking clarity. Stars like Theta 1 Orionis C live fast and die young. In another few million years, a mere extra year or two on our human lifespan scale, it will exhaust its nuclear fuel and end its life in a catastrophic supernova explosion. That explosion will dwarf the power of its stellar wind. It will likely be the final blow that completely shatters the Orion Nebula as we know it, blasting the remaining gas of the veil in the molecular cloud far into interstellar space, ending its brief, brilliant era of star formation and enriching the galaxy with heavy elements for the next generation. So, when you look at Orion, remember, you are seeing a month-long event in the 40-year life of a star. You are seeing a place of simultaneous creation and destruction, where the brightest light is also the most violent force, and where the entire epic story, from birth to climax to impending end, is unfolding in what amounts to a cosmic moment. It is a temporary masterpiece, and we are impossibly lucky to be here, right now, to see it. So, we've seen the birth, the brilliant life, and the violent weather of this nursery, but all stories have an ending, and the future of the Orion Nebula is not a mystery. It is written in the immutable physics of the very stars that make it glow. To understand its fate, we must look squarely at the rulers of the trapezium cluster, especially Theta 1 Orionis C. Their future is the nebula's future.
These stars are the rock stars of the cosmos. They live by a single, blazing principle: live fast, die young, and leave a spectacular corpse. They are nothing like our steady, reliable sun. Our sun is a frugal saver, carefully burning its hydrogen fuel over billions of years, planning for a long retirement. A star like Theta 1 Ori C is a profligate spendthrift. It burns its fuel with a kind of glorious, wasteful desperation. Why? Because of its immense mass. Gravity is the engine of a star, and the more mass you have, the more gravitational pressure you create at your core. For Theta 1 Ori C, with its 40 solar masses, the core is a crushing, hellish environment of unimaginable pressure and temperature. This forces the nuclear fusion reactions, the process of mashing hydrogen atoms together to make helium and energy, to run at a frenzied, runaway pace. It's the difference between a cozy campfire and a nitromethane-fueled dragster engine. The dragster produces mind-boggling power, but it burns its entire fuel load in seconds. Theta 1 Ori C is a cosmic dragster. While our sun will happily burn hydrogen for about 10 billion years total, a star of that mass exhausts the hydrogen in its core in only 4 to 6 million years. We've already established these stars are about 1 million years old, so in cosmic terms, their clock is already ticking loudly. They are in the prime of their short lives, but the end is, relatively speaking, just around the corner. What happens when the hydrogen fuel in the core is all gone? The fusion fires there sputter and stop. Without the outward pressure from fusion to balance the immense inward crush of gravity, the core begins to collapse. But this collapse heats things up even more, like pumping a bicycle tire and feeling the pump get warm. This new, intense heat ignites a new, larger shell of hydrogen around the now inert helium core. The outer layers of the star react to this fierce new energy from the shell by swelling up and up and up. The star transforms into a red supergiant. If Theta 1 Ori C were placed in our solar system at this stage, its swollen outer atmosphere would likely extend past the orbit of Jupiter. It would become a monstrous, cool red ember in the sky. But this is just a prelude. The core continues to collapse, getting hotter and denser. Once it reaches a critical temperature of about 100 million Kelvin, a new fusion reaction kicks in. Helium atoms begin fusing to make carbon. This releases energy and stabilizes the core again, but only temporarily. For a massive star, this begins a desperate, layered cascade. When the helium is exhausted, the core collapses again until it's hot enough to fuse carbon into neon and magnesium, then oxygen, then silicon. Each fusion stage produces a heavier element and lasts for a shorter and shorter time. The silicon fusion stage, which creates iron, might last only a single day. And here, we reach the end of the line. Iron is a cosmic dead end. Fusing iron atoms together doesn't release energy, it consumes energy. So, when an iron core accumulates in the heart of the star, the final, most powerful fusion engine of all sputters and dies. Instantly, the balance is shattered. Gravity, which has been held at bay for millions of years by these successive fusion fires, wins the war in a fraction of a second. The iron core catastrophically collapses. In less than a second, it crushes down from something the size of Earth to a ball of ultra-dense neutrons only about 20 kilometers across, a city-sized object. The outer layers of the star, suddenly with nothing underneath them, come crashing down at nearly a quarter the speed of light onto this unimaginably hard new surface. The impact is so violent it creates a rebounding shockwave of unbelievable energy. This shockwave, turbocharged by a flood of neutrinos pouring out of the newborn neutron star, explodes outward. The star is blown apart from the inside out. This is a core collapse supernova, and the language we use for it always fails. It is not an explosion, it is the explosion. For a few weeks, this single dying star can outshine its entire host galaxy. In a matter of seconds, it releases more energy than our sun will over its entire 10 billion-year lifespan. It is the most violent, luminous, and transformative event in the present-day universe. Now, imagine this not happening to one star, but to several, to Theta 1 Ori C and its massive trapezium siblings within a relatively short span of a few 100,000 years. This is the final act for the Orion Nebula.
The first effect is pure, unadulterated destruction. The shockwave from the first major supernova will hit the remaining structures of the nebula like the hammer of a god. Those beautiful, sculpted pillars, the delicate filaments of the Orion Veil, the glowing ridges of gas, all of it will be caught in a tsunami of energy moving at tens of thousands of kilometers per second. They will be shredded, vaporized, and swept away. The supernova will completely overwhelm the gentle ionization glow from the surviving stars. For a brief, terrifying moment, the supernova itself will be the only thing visible, a new blinding star in Orion's sword that might even be visible from Earth in broad daylight. Within a few 100,000 years after the first explosions, the process will be complete. The gas and dust that once constituted the distinct glowing cloud of M42 will have been blasted outward, expanding into a much larger, much fainter, and rapidly dispersing shell. The Orion Nebula, as a coherent, bright object, will be gone. It will have returned its material to the general interstellar medium of the Milky Way galaxy, the thin, diffuse soup of gas and dust between the stars. But, and this is the most important but in all of cosmic history, this is not just an end. It is a necessary, glorious, and creative conclusion.
Because while the first effect is destructive, the second effect is generative. It is why we are here. Inside the furnaces of those massive stars, during their brief lives, they were cooking up the ingredients for everything we know. Through the successive stages of fusion, hydrogen to helium, helium to carbon, carbon to neon, oxygen, and silicon, they forged all the elements up to iron. But the supernova explosion itself is an even more potent alchemist. The insane energy of the collapse and shockwave creates conditions so extreme that atoms are bombarded with neutrons in a furious process called the R process, rapid neutron capture. In this maelstrom, in a matter of seconds, the atoms are built up into elements heavier than iron: cobalt, nickel, zinc, silver, gold, platinum, uranium, the entire periodic table. And then, the supernova does the most important job of all. It scatters these newly forged elements far and wide. It pollutes the surrounding interstellar medium with this rich, heavy ash. It pollutes the galaxy with the stuff of planets and, ultimately, life. Think about what you are made of. The calcium in your bones and teeth, forged in a massive star during its silicon-burning phase and scattered by its supernova. The iron in your blood that carries oxygen, forged in the last dying days of a stellar core. The iodine crucial for your thyroid gland, a product of the R process in the supernova blast. The carbon that is the backbone of all organic molecules, forged in the belly of a red giant star. Even the gold in a wedding ring or the uranium in a power plant are the ashes of stars that died billions of years ago. This is the beautiful cyclical part. The Orion Nebula will die, but its death will fertilize a vast region of the galaxy. That enriched gas, now carrying the elemental signature of the trapezium stars, will mix and swirl with other gas for millions or even billions of years. It will be part of the great galactic recycling system. Then, somewhere, perhaps on the other side of the galaxy, perhaps in a future spiral arm, gravity will begin its work again. A ripple in the galactic density or the shockwave from another supernova will compress a new giant molecular cloud, and within that cloud will be atoms of oxygen, carbon, iron, and gold that were once part of the Orion Nebula. As that new cloud collapses to form a new generation of stars, a new cluster, perhaps with its own glowing nebula, those heavy elements will be incorporated. They will form rocky planets around those new stars. They will become the minerals in the crust of those planets, the metals in their cores, and the dissolved elements in their oceans. This is the incredible connection. We are not just observers of this cycle, we are products of it. Our solar system formed about 4.6 billion years ago from a cloud that was undoubtedly enriched by many massive stars from many previous generations of nebulae just like Orion. The iron in Earth's core, the silicon in its rocks, the oxygen in its water and air, it all came from stars that lived and died long before our sun was born. We are literally made of star stuff. So, when you look at the Orion Nebula, you are looking at a chapter in a story that is also your own origin story. Its brilliant present is our distant past. Its violent, glittering future is the creation of the raw materials for future worlds and perhaps future beings who will one day gaze up at their own night sky, find a glowing nebula, and wonder where they came from. The Orion Nebula is a temporary masterpiece. It will fade. But in its fading, it will broadcast the seeds of future masterpieces across the galaxy. It's a cosmic cycle of death and rebirth, where an ending is always a beginning in disguise. And with that, our deep dive into the heart of the Orion Nebula comes to a close. From its birth in a cold, dark cloud, to its dazzling present as a stellar factory, to its explosive future that will one day seed the cosmos, it truly is a place where the entire story of the stars plays out on a single, magnificent stage. I hope this journey has filled you with as much wonder as it does me every time I think about it. If it did, please let me know by giving this video a thumbs up. It really helps the channel. And if you haven't already, hit that subscribe button and ring the notification bell so you don't miss our next adventure across the cosmos. Now, I'd love to hear from you. Where are you watching from tonight? Are you in a bustling city or out under dark rural skies? Can you see Orion from your window right now? Drop a comment below and tell me your location and the time. Let's see how far and wide our community of stargazers spans. Thank you so much for watching and for sharing this journey with me. Until next time, keep looking up. Remember, we are all, every single one of us, made of stardust forged in places just like this. Good night and clear skies.